So the topic we're going to get into today, okay, is limits. Okay, and limits, like I said, is going to be a new topic. That's something maybe you guys really haven't talked too much about in the past. I don't think this is something that you've not seen in other classes. So this is our first kind of, fully pre-calculus topic. And the reason why we talk about it in pre-calculus is because it's fundamental to calculus. Okay. The concept is fundamental to calculus. For those of you, back when we were, when I had to do like course recommendations, and I kind of just did blanket recommendations for all you guys because I really didn't know you, right? And I'm still figuring you guys out, and stuff. As far as what I would recommend you for. This is a kind of crucial concept right here. I'm not trying to say that I can make you choose one calculus or another. You get to make that decision. But if you want a pretty good metric of not what calculus will be like, but just some of the ideas from calculus, this is this topic that we're going to be studying today and the next couple of days will be kind of beneficial. Please don't freak out if you're like, oh, I don't get any of this, I should not take calculus or anything. I mean, that's not necessarily the case. It's just this is kind of a introduction to some calculus topics and stuff like that. So even with talking to Mr. Goff too, he would say this would be a good kind of way to gauge yourself as far as what calculus will kind of feel like, at least in the start. And then it will get easier, of course, too. I'm not saying this is really hard, but I'm just saying, you get the hang of it and stuff, too. Because this is a bit of a weird idea. So, with that preparation, let's take a look here at the idea. And hopefully I can get the idea across in a clear way, too. So let's consider a rational function we have here. And I'm just going to come up with an example that I've got pre-prepared. Okay, so let's say we've got a function here, g of x, and it's equal to 2x squared minus 5x plus 3 all over the quantity x minus 1. Okay. Right, and so what I'm going to actually do here is I'm going to graph this on my graphing calculator, okay? And, if you haven't worked with rational functions before, you may expect some sort of craziness here. And sometimes we do get some craziness. And in fact, yeah, you guys will want to have your calculators handy for this. So if you do have your calculator, great. Does anyone not have a calculator? I can let you borrow one. Okay, so 2, 3. Okay. Let me see what I've got here for you. Borrow this one. Okay. So, we'll graph this thing. Make sure you use, appropriate parentheses here. So, for example, sometimes I'll see students type in. Well, actually, yeah, be careful what you type in here, right? The fraction bar there, right, kind of groups the numerator. So you want to make sure you have the numerator group with parentheses. Okay, and you also want to group the denominator here too. So we don't want to just put in divided by x plus 1 like that. Okay, right, we have to put parentheses around the denominator. Okay, so parentheses around the numerator, parentheses around the numerator, parentheses around the denominator. And you graph it. And, wait a minute. I graphed x plus 1 instead of x minus 1. There we go, okay. So it looks just like a line. That's pretty, I don't know, I feel like that's out of ordinary for what we've got up there, right? You'd think there'd be some crazy looking graph here, but it looks like it's just a line. And in fact, it is a line, but we have something interesting happening here. So I'm going to sketch this graph here. At what particular x value here do we expect there to be some issues? 1. Yeah, why do we expect value issues at 1? Yeah, the denominator is x minus 1, so we'd expect that we're going to have a 0 in the denominator at x equals 1. In fact, we also have a 0 in the numerator. So if we try, if you guys didn't know this, by the way, if you press second trace and you go to the value command, the very first command there, you can actually like have your calculator, you can like type in an x value and then the calculator will spit out the y value. So if we try and type in 1, for example, you'll see that the y is left blank. Okay, there is no value there. But if you look at the graph, it looks like there should be, right? It looks like there should be something there. All right, and so the idea here is that there is actually 4, 2, 3. Let's see here. So I think the graph of this thing, if I remember correctly. Oh yeah, okay. So we're going to graph this thing in just a second here, but let's fill in a table and kind of see what happens. As x approaches 1, right? Obviously, we cannot evaluate the behavior at 1. At 1, you can see our calculator again gives us no answer, right? The y is equal to blank, okay? But what happens as x approaches 1? Maybe we can get an understanding of what's going on here as we approach 1. So let's do that here, and let's make a little chart to help ourselves out here. So I'll put like some x. I'll make like a horizontal little chart here. So we'll say x and j of x like this. Okay. And let's approach 1. Now, to approach 1, we can approach 1 from 2 different directions, right? We can approach 1 from the left-hand side of 1, you know, values that are less than 1. So for example, a value that's less than 1 but close to it would be like 0.9. And then we could get even closer and do like 0.99. And we could do like 0.999, and then I guess I'll kind of say that's good enough. And then I'll put the 1 in there, right, because that would be like at 1, maybe. And we can also approach 1 from the right-hand side, from values that are greater than 1. So like just a little bit greater than 1 is, you know, 1.001, and then we could try like 1.01. That's a little further away from 1 still, and then we could go even to like 1.1, for example. We already know that at 1, right, we're not really sure what's happening. We're kind of like unsure about that because we plug 1 in, it gives us an issue. To do this, you kind of have a couple options. One thing you can do is what I just showed you in the calculator there. You can press second trace, use the value command, and just type in like 0.9 and hit enter, and you get negative 1.2. And you could repeat that with 0.99, 0.999, so on and so forth. There's another tool, though, on our calculator that we can use is the table. Okay. Now, your table, let's see here. Most of you guys, I'm going to assume, your table is going to look something like this, where it just counts by 1s, right? And you would only be able to get, you know, whatever values it has here. But of course, we're not counting by 1s here. We're counting by like different decimals and stuff like that. So again, I don't know if it's something you guys have seen before, but I'll show it to you here now. You can change the way your table sets itself up by pressing second window. Okay, so just like you press the window button to change how the graph, the coordinate plane is set up, you press second window, and you can change how the table is set up. Now, I don't really care so much about where the table starts, or the delta table, that is the change, right? But instead I like to go down here to the independent, and instead of automatically having the calculator fill in the independent variable, that would be like the x variable here, right, is independent, we're going to have it ask us what the independent variable will be, and then we'll let it automatically fill in the dependent variable. So now if we go to our table, it's empty. Well, that's because it's waiting for us to type in x values. So for example, I could type in 0.9, okay, it just shows up here, and I hit enter, and it spits out the matching y value. All right, so I can use 0.99. Hit enter, and then it spits out the matching y value, negative 1.02. So this is very handy when you have to type, we have to like put in a bunch of different inputs into a single function there. Okay, I can type in 0.999, hit enter, and then I get negative 1.002. Okay, and I can type in 1.001 and get negative 0.998, and then 1.01, negative 0.98, and then negative 1.1. Sorry, not negative 1.1, 1.1. I get negative 0.8, it looks like. Okay. But again, if we type in that 1, if we try and type in 1 into our calculator here, our calculator gives us an error. Okay. By the way, too, you know, because of the way this table is drawn, the most it can kind of fit on here is like maybe 3 decimal places. But if you arrow over to a particular value, down here on the bottom you'll get a more precise decimal, because sometimes it's rounding and stuff like that. In this case, these are all displaying 100% accurate, but sometimes these don't display accurately, but you can highlight them and it'll show down here what the more accurate decimal would be. Okay, so what does happen as x approaches 1 here? What are we approaching in the y values? What y value are we approaching? What value of g are we approaching here? Negative 1, right, yeah, okay. As our x values, 0.9, 0.99, 0.999, as those get closer to 1, our y values get closer and closer to negative 1. Right here it's negative 1.2, and then closer now, negative 1.02, and then closer still, negative 1.002. And then as we get closer from this direction, right, so 1.1, that's a tenth away, we have negative 0.8. But then when we're 1/100th away from 1, now it's negative 0.98. And then we're 1/1000th away from 1, we're at negative 0.998. Okay, so very close to negative 1 on either side here. So we want to say that this equals negative 1, or it approaches negative 1 at least. Okay. And so the way the graph is actually going to look here, we're going to actually have, we have to have a hole at point 1, negative 1, and then I think, let's see here, I believe it goes something, you know, kind of like, I forget exactly how, okay. I think it goes 1, 2, I don't know, something like that basically is what it looks like. It's not a super accurate graph, but we have a hole there is the idea. Okay, and we'll talk more about holes as well. Okay, it's a type of discontinuity, right, in our graph. So, in summary here, we can kind of say that g of 1, okay, is indeterminate. Okay, you get 0 over 0. But as x approaches 1, okay, and you know, normally when we think about approaching something, we normally think about approaching it from, you know, from like smaller values, right? We're kind of like going from left to right, we're going from like, you know, from lower values up to 1. But we also mean, when we say approach in this case, we're talking from the left-hand side and from the right-hand side. As x approaches 1, g of x moves arbitrarily close to the value of negative 1. Okay, so what do I mean by arbitrarily close there? Well, believe it or not, there is like a mathematical definition for arbitrarily close, like, you know, define and stuff like that. And the basic idea about arbitrarily close is this, right? Some of you may take more convincing than others to say that it goes to negative 1, right? Some of you might be sticklers. You might be like, Mr. Widmeyer, we can't say that this is approaching negative 1 because this value is not negative 1 and this value is not negative 1. Yes, they're close, but they're still off by, you know, 0.002 in each case, right? So you can't really say it's negative 1. They're off, you know, they're off by a certain amount. And so when it comes to arbitrarily close, you know, you can tell me, Ms. Widmeyer, I would need you to get so close that you would need to be within 1/1,000,000th of 1, and negative 1. And then I'll say that, you know, it's okay, sure, it approaches negative 1, right? And so the idea of arbitrarily close is that you would give, you know, you would say I would need to be convinced, and you'd have to be this close, and the idea is that we could actually get that close. Okay, so no matter how close you need to be to negative 1 to be convinced that it's going to approach negative 1, we can get that close. That's what arbitrarily close means. Okay, some people might need to be convinced by being only 0.002 away. Some people might need to be convinced by being, you know, 1/1000,000th away or 1/1,000,000th away or something like that. We could do that. Okay, we can get even closer. And I can just, you know, if you look at your calculators here, the tables, right? I could do like 1.00000000001, you know, like that. Type that in, hit enter, and you'll notice the calculator, it just kind of gives up at that point and says that it is negative 1. Now, granted, it's not precisely negative 1, but it's just close. The calculator says it's negative 1. Okay. So that's the idea of a limit. It's the kind of like the value of the function as you approach a particular x value. Okay, so let me give you the official kind of mathematical definition here. That's the concept of a limit. Okay. So, if f of x becomes arbitrarily close to a single number, and we'll call it capital L, as x approaches a number C, from either side. So again, there's that idea, right? We don't want to just think about approaching that C value from the left-hand side, from lower values. We're also thinking about approaching it from the right-hand side. Okay, so from either side. Then the limit of f of x as x approaches C is L. Okay. So there's kind of two numbers here that we're talking about approaching, right? We have our x value. So like in the case back up here, right, the x value that we were approaching was 1. Simultaneously, though, to that x value approaching 1, okay, our y value was also approaching a value, okay, a number, in this case -1. So the c up here, the c that our x was approaching, the c value that our x was approaching was 1, and the capital L value, the limit that our function was approaching, is -1. Okay? So x was approaching 1. Our function, our capital L limit value, was -1 that we were approaching, right? Both sides were approaching that. Okay? So obviously that's a lot of words to write out, and we like to use symbols and shortcuts and abbreviations. So the way we symbolically say that is the limit as x approaches C of f of x equals L. Okay, and this will be one of the first major units that you touch on should you decide to move on to calculus next year. This is like one of the very first units you'll touch on. Okay, and in this particular case, okay, so that's like the the very official mathematical way to see it. So in this case, if we apply all the stuff that we have from our example here, okay, we can say that the limit as x approaches 1 of 2x squared minus 5x plus 3 over x minus 1 is, well, -1, right? We kind of analyze that from our graphing calculators there. Okay. The y value that this function approaches as x approaches 1 is -1. Okay. So it is similar to evaluating the function. It's similar to just plugging a number in and getting out the y value, but it's not the same. Okay? And this distinction can cause some confusion, especially early on. So, I'll try my best to make sure that doesn't happen here. So let's try another one. Okay, now we've kind of beat that one to death, and let's see if we can come up with this one here. So let's, again, evaluate. And now I'm going to use this limit idea, this limit notation here, overtly. Okay. Now, the way that we evaluate a limit, all right, well, there are multiple methods, right? The method we just used up here was a table. And we're going to use a table again down here, and then we'll develop some more tools for evaluating limits after it. But let's do this here. So let's by completing a table. Okay. So we'll do that same kind of table that we had before. So we'll do y and x, and then I'll just say that that function's f of x. We really don't have a name for it, but. Now we're approaching 0 with our x values in this case. So if I want to pick values to the left of 0, I got to pick negative numbers. So I could start with something like -1 if I wanted to, but then I could do like -0.1, right? That gets even closer to 0. And then I could do like -0.01, that's even closer to 0. And if I wanted to be like -0.001, and then there's 0. And then I want to go to the right of 0. Okay. Well, then immediately to the right of 0, I'm just going to put the positive 0.001, and then I'll do the 0.001. Sorry, I think I just repeated myself. I did. Sorry. 0.01. There we go. And then 0.1, and then 1. Okay. So go ahead, use your calculators, fill in that table. All right. Go ahead, use your calculators there and complete that table, and I will do the same. Be careful about how you type that function into your calculator too. Okay. Oh, and your old table values, by the way, you can actually, you can either hit the delete button to get rid of those, or you can just type over top of them too, whichever one you want to do, and it'll replace it. So anyway, go ahead and fill those table values in, and see if you can figure out what the limit is, or see if you can analyze what the limit would be based off this information. Question? Yes. Yes, you want to be approaching 0. No. The x values are approaching 0, right? See, it's the limit as x approaches 0. And then what is then y approaching? So yeah, there's two different numbers we're approaching here. X values should be approaching 0. Y values are approaching a mystery number whose answer will be the limit, right? Or whose value will be the limit of this thing. Error. Okay. That's weird. You have x minus 1 and it's x plus 1. I think I'll do this in a few minutes. Make plus 1. And now I'm going to do this. You go back to your table. Alright, I was going to say, I'll let you make that decision. Alright, if you're fine, I'm fine. Right? Any other questions? Good, okay. Why did you give me 1? Oh, because what we're approaching, what value we're approaching here. At that 0, you're going to get here. So for these numbers, yes, that would be right. But these numbers aren't correct. So we need to go to the you load the parentheses too soon here. You want to go to the parentheses right here. Now the minus 1 equals the denominator. No, but here's the good news. We can just the table will be fixed. So if you want to rewrite them all, you can. I mean, you can actually do it here. So now
I did all of them.
I kind of just did whatever, yeah.
I gave all 4 calculated.
as you approach 0, from the left to the right, what's the y?
4 decimal places, man. You are all hard workers. You are going to be on the forefront.
Okay.
Hopefully in the workforce.
So
No.
there's our table filled in. Okay, and so we can then say, with, pretty good certainty, that the limit as x approaches 0 of the square root of x plus 1 minus 1 is what? 2. Okay, so that's the limit. Okay, and this is a legitimate technique that this will follow you into calculus too. There are some limits that we will be unable to evaluate analytically. Okay, so that's not what we're doing right now. This is like numeric, I would say, numeric kind of analysis of a limit, because we're just using a table, we're plugging values in, and we're kind of like seeing what the numbers approach. Okay, there are like sound analytic ways to do this, like you would solve an equation kind of thing, right? We have like mathematical techniques for solving limits too. But sometimes we don't. Sometimes those limits, those methods will fail us, and we will have to rely back on numeric kind of analysis too. So this is something that will follow into calculus too. It's not like this is the baby step and you'll never use it again kind of thing. This will also be viable. Okay, so keep that in mind. Now, bless you. Speaking of different approaches to evaluating a limit, there are 3 that we will be looking at. Okay, and 2 today we'll talk about, and then the third one we'll get to, I believe, later. So, okay, but that table approach, that is a legitimate approach, and should you have a graphing calculator, feel free to use that. Because that's a possibility. Okay, so that's a totally legit approach. So like I said, we called that the numeric approach. That's the table of values. That's what we just did. Okay. Later, we will also talk about the graphical approach, and that's when you basically just kind of look at the graph and evaluate the limit based on what you see in the graph. I mean, we kind of did that, excuse me, we kind of did that before, I can do here with this one. So for example, here's an example of the graphical approach. This is the function that we just, whose limit we just evaluated. If I, were to like trace here, and you can see that at x value of 0, my y value has no value, because at 0 we have a problem. But if I go just to the left of 0, I'm now at negative 2.12, and I can see my y value is like 1.88. And if I go immediately to the right of 0, so I'm at positive 0.212, I'm now at 2.1. So it's similar to how we use the table. You look at what's to the left of that, limit that you're approaching, x value you're approaching. You look to the right of the x value that you're approaching, and you see the y values go from, just below 2 to just above 2. So you think it's gonna, you would imagine, oh, it's gonna approach 2 there. Okay, so that's what you do. And if you want, you could like zoom in more with your graphing calculator and get more precise values. But again, we already know the limits 2 anyway. So just look at the graph. All right, and then the third one, and the one that we're gonna use probably the most. Okay, the one we'll use the most, or the one that's going to have the most use in our class, is the analytic approach. Okay, and that's where you actually like the traditional kind of like doing the math kind of thing. Although what I would argue, the table stuff was doing math as well, but this is like what we're more familiar with. Okay, and in this, we're going to require either algebra or calculus. So obviously, we'll be skipping the calculus part of the analytic approach. But in calculus, you'll learn about something called L'Hopital's rule. But for now, we're going to stick to algebra because we don't know calculus yet. This is pre-calculus. Okay. One thing to note is that 1 and 2 are methods of approximating a limit. Okay. Yes, we're saying the limit was equal to those things. You know, those two limits we found earlier, we're saying they were equal, and in fact they are equal. We can actually, but that's because we can prove those things using analytic approach as well. Okay. So 1 and 2 again, we use the table to give an actual limit, but really it's an approximation. But we could solve 1 and 2 using an analytic approach that would give us those exact values. So that's why we can say they are exactly those things. Okay, so how do we go about evaluating limits analytically? Okay. Just like when we were factoring, right, and we came up with a bunch of tools to use in different scenarios, right? Same thing with evaluating limits. We are going to kind of develop some tools for different situations, different scenarios. The main tool we want to use, so in some cases, okay, the limit can be evaluated by direct substitution. Okay. And so what I mean by that is this. The limit as x approaches c of a function, in some cases, is equal to exactly the value of the function at c. Okay, so this is where I said, it can get not confusing, but difficult to distinguish sometimes, right? Because there's this tool called direct substitution where evaluating the limit is precisely the same thing as plugging in c to the function and just evaluating the function at that point, okay? But this is not always true. The exception here, this is true if and only if f is continuous. Okay. And we know, hopefully we have like a basic idea about what continuity means, right? Continuous in a basic sense means that the graph has no holes, no jumps, no breaks, no vertical asymptotes, nothing like that, okay? It's just one nice smooth graph, okay? You could like trace it with your pen or pencil without having to pick it up in order to continue graphing, right? That is the example. That's like a basic understanding of continuous, and I think we will get to the definition of continuity. I'm not sure. You will definitely get to the definition of continuity in calculus, though, for sure. Okay, I kind of forget, but we'll see. All right, so, question.
How do you have a limit?
So, the idea of a limit can be applied to a continuous function. That's all the idea is. So, right. It makes, the idea of a limit makes more sense when we go back to a problem like this, where there was a problem at 1, and so we wanted to approach from both sides, so it makes sense. If we can't evaluate at 1, we can approach 1 from either side. It doesn't make so much sense to evaluate a limit when the function works everywhere, but you can evaluate the limit of a function anywhere. Does that make sense? Okay, so does that kind of answer your question, I guess I should say. Yeah. It's not, it's not very impressive. So, I'll just show you here. So, as an example of this kind of thing, right, so we can, we'll do some problems here. We'll say evaluate the given limits. Okay. So, in a very basic sense, and this might seem silly, but let's say we want to take the limit as x approaches -4 of the function x. Okay? So x, right, the graph of x is a line, slope of 1, y-intercept of 0. The limit as x approaches -4 of x. Well, is x continuous? Yeah, right, it's just a nice line, right? So we have no problem. So we can evaluate this limit just as if we were evaluating the function at -4. So what I can just do, I can just plug -4 in here, and so the answer is -4. Okay, it's that easy. Okay. Let's see here. I'll try another one. The limit as x approaches 3 of x squared. The limit as x approaches 3 of x squared. Is x squared continuous? Yes. Okay, so we can direct substitute in, and so this limit would be equal to what? 9, right? Because it's 3 squared, so it'll be 9. Yep, we plug the 3 in, and I'll go ahead and like show that here. Maybe that's more steps than you need to see, but there it is. It would be equal to 9. Alright, so that's that in a basic sense. Let's try another one here. The limit as x approaches 2 of the function 3. Or f of x equals 3. So, is the function f of x equal to 3, is that a continuous function? What does f of x equal to 3 look like? It's a horizontal line, right? So is that continuous? Yeah, okay. So what's the limit here? 3. Yeah, it's just 3, right? No, you know, any limit. The limit as x approaches any number of 3 will be 3. Like it's going to give you the constant 3. Here, number 1, the limit as x approaches any number of x will just be that number, right? And then for this one, it's going to be the number squared. Okay, so it is very similar. It is very similar, deceptively similar to evaluating the function at a particular point. But the limit as x approaches 2 of x squared plus x minus 6 over x minus 2. Does direct substitution apply here? Is this function continuous? Where will it be discontinuous? At 2, right? Because 2, the value of 2 will make this function undefined. Okay? So then how do we evaluate this limit? We can't use direct substitution. Well, what can we do to this function here? What's that? Simplify it. Yes, the numerator factors, does it not? What does it factor to be? X minus 2, x plus 3. That's right. Over x minus 2. Okay? Now, the x minus 2's cancel, right? Can I evaluate this limit? Is x plus 3 continuous? Yes. I can use direct substitution. Plug the 2 in for x. 2 plus 3 is 5. So this limit is equal to 5. Okay. Notice what is missing here that was not, notice what's missing here that was present yesterday when we were evaluating and simplifying those rational expressions. When I canceled the x minus 2's yesterday, I would have had this is equal to this with the exception that x is not equal to 2. Okay? But I don't need that exception when I'm evaluating a limit. I don't need the exception because I am never going to be at 2. A limit is only ever approaching 2. since it only ever approaches 2, I can say that this expression and this expression are the same thing. Okay? Because at 2, we're never going to equal 2. A limit does not ever get to 2. It only ever approaches 2. And so I can say this is similar to this because these two things are equal at x values that are not 2. Right? These two things are the exact same at x values that are not 2. And since we're only approaching 2, we can say they are exactly the same thing. And so then 5 would be our answer there. So the limit is 5. Okay, the limit exists and it is 5. All right. All right, so let me have you all try one then. So the limit as x approaches 1 of x squared minus 1 all over x minus 1. So give that one a try. Give that one a try. And if you don't believe me, you can also use your calculator to check too, right? If you want, if you want some extra convincing, it's like this for minus BS. You can look at your calculator, okay, and you can see that it will approach, for example, number 4. If you approach 2 with your x values, you will see that the y values approach 5. Okay.
Oh, x goes to 1, so we're trying to make 1 doesn't plus 1.
Yeah, try to be careful how you're factoring that because x as x approaches 1. Positive. Good. Okay. So again, this function that we're evaluating here, right, is discontinuous, or it's not continuous at 1, right? Or it's going to be dividing by 0. So to evaluate this limit, we cannot yet use direct substitution, but the numerator factor is x minus 1, x plus 1. The denominator is still x minus 1. Those will cancel. That will be equal to the limit as x approaches 1 of x plus 1, which is then just 2 now by direct substitution. Okay, and if you use your graphing calculators there, you can see that the table will also yield a similar result. It's just a matter of the y values will approach 2. Okay. Questions on any of that? All good? All right, let me give you guys some practice here then because it's so different. All right, so page 858. I would like you to try numbers 7, 9, 13, and 53 to 61 odd. And then also page 868, numbers 9, 12, 14, 15, and 19. Okay, now, a bit of a little just tip here. I think the second page set here, so the stuff that starts on page 868, that's like what we just did with like direct substitution. So if you want to practice the direct substitution more, you want to maybe consider going to 868 first and then hitting 858, which is just going to be the tables, I'm pretty sure. Okay? So if you want to do more direct substitution practice, page 868 is where you want to go. If you want to just do the table practice, page 858 then is where you want to go. Okay? Alright. And I highly, highly, highly recommend you get these books out and get practice here in class because, I don't want you to get home over the weekend and be like, I forget everything because this is due Monday too, so, So I highly recommend you get started on some of these just to make sure you got it.